Thank you for the introduction. Good morning, everybody. My name is Xianglin LIU. I would like to make a small talk on behalf of my team in Fugro Satellite Post. The title of my presentation is Fugro Next G4 PPP-IAR service with fast convergence. The contents of my presentation, including a bit history of Fugro PPP service evolution and project goal, latest developments and the infrastructure that we use to provide such a service. And I will also display some of fast convergence and accuracy results that we got recently from this service. Finally, I will list a couple of conclusions and outlook. This slide demonstrates the history of Fugro positioning service, not to mention very early developments. From 1906, Fugro started the satellite-based broadcast beams to broadcast code-only L1 VBS corrections for differential GPS positioning. And in 2001, Fugro had dual frequency code and phase DGPS along the coast of major continents. In 2006, we start to broadcast third-party GPS orbit and clock corrections. And in 2009, we start to compute our own GPS and Glonass orbit clock and provide PPP service. We provide G2 Plus ambiguity-fixed PPP service in 2015 by broadcast additional biases, and then BeiDou and Galileo orbit clock are added to the G4, so-called G4 service in 2015 and 2016. Gradually, we provide full support for 4 global satellite constellations. In 2021, we launched Fugro Spacestar LEO PPP service and Tomcro for 10 synchronizations through PPP. In March of last year and March of this year, we launched Next G4 service that we add the BeiDou and Galileo phase slice for dual frequencies and 3 frequencies. I will focus on this service in this presentation. In last decades, Fugro made a great effort to involve our GNSS PPP service from original lower accuracy and slow convergence to higher accuracy and fast convergence, as we can see from this figure. So the horizontal axis shows our efforts for convergence, and the vertical shows our efforts in the accuracy. To provide to provide the good service, we first compute satellite orbit clock in the service site, and then derive satellite phase and code biases in the service site, and further realize the fast ambiguity fixing. And we will also implement the multi-layer process of integer integrity monitoring and quality control. To provide the good service, we rely on Fugro infrastructure, shown here. Yeah. Fugro SatPost has maintained more than 100 reference sites globally and 6 global airband geostationary satellite broadcast beams and 2 fully redundant network control centers. The orbit clock corrections plus phase bias that we calculate in the server side are sent to our 2 NCCs and uplinked to geostationary satellites and then broadcast to our marine clients. The mobile receivers have our engine, computation engine enabled to calculate precise coordinates with fast convergence. From this slide, we will present a few pieces of results that we added, we got it. And let me show the position results with dual frequencies firstly, and the blue. The blue is the ambiguity-float solution, and green is the ambiguity-fixed solution you can see here. So this is 3 components, and this is the age of the corrections, and this is the used satellites. And we can see that the green curve is much flatter than the float one. We made a statistic for jumbo receivers in our network. So left figures, left figures float solution, and the right one is ambiguity-fixed solution. So you can see the convergence converged from, reduced from 10 minutes to 5 minutes. We also made a statistic for another receiver, which is sequential receiver. So the same as the last slide, so we can see that convergences are short from 10 minutes to 5 minutes. And from these figures, we start to show the multi-frequency position. So we have these sites. We have this site that, again, the blue is the float solution and the green is the fixed solution. We reset it every 1 hour. So we can see that they are fixed quite often, quite fast. We made the statistic for this site for 10 days. So we can see that in left figures shows convergence and accuracy from horizontal component, where the right one shows results for the vertical component. Notice that this is 95% confidence level. The horizontal component can reach 5 centimeter accuracy. Actually, it's better than 5 centimeter accuracy in only half minutes, 29 seconds. At the same time, at the same period, the vertical reached to almost 5 centimeters. So we also did, for another site, we can see that for time series of 1 day and statistic for 10 days. So this is for single site, but we also made this convergence for the whole network. So a lot of sites, we can see that convergence time are about half minutes. Some of them even shorter than half minutes. And notice that this is 95% confidence. So this is accuracy globally, even including the resets in the statistics. So we can see that most of sites are better than 1 to 15 millimeters, 10 millimeters to 50 millimeters in 95% level in horizontal, and 30 millimeters to 50 millimeter accuracy in vertical component. Currently, the ionosphere simulation is experiencing very high activity. We also investigate the performance of our next G4 multi-frequency surface during the simulation near the equator. Look at the red sites that, particularly in the Asian Pacific region. So we can see we also reset during the simulation period. So this is the period. We can see that. So you can see the use of satellites are oscillated very often in that period. So even when we reset the receivers, they can be quite quicker to fix ambiguities. And we also had sites for other sites in the Asian equators. So you can see that the ambiguity-fixed solution can be fixed very quick. Use our next G4 multi-frequency surface. So we also did a bit of dynamic test for the agricultural sectors. So we can see we use a single antenna connected with 3 receivers. That way calculate the PP solution individually and compare each other. So this is mobile 2 respect to mobile 3, and this one is mobile 3 with respect to mobile 1. So we can, we could see. This is another dynamic test that will make a car navigation in the Delft and Den Haag. So if we do not use any technology, use standard PPP solution, so we can see a lot of reset during the past the bridge or the trees. But if we use our fast convergence reunitization, we can go through a lot of bridges and use our multi-frequency service. We can see solutions are converged quicker, and even use local ionosphere in the SSR domain. We can get much fast convergence and the fixed rate also increased from. Yes, do not go on. Yeah, fixed rate also improved from 61% to 91%. So conclusion, Fugro negligible surface is on air, and we are being broadcast on all 6 beams. And both multi-frequency and the multi-constellation play a crucial role in fast convergence. And with our latest development and service, convergence time has been reduced from approximately 12 minutes to the 3 minutes, with the accuracy improved to 2.5 centimeter horizontally and 5 centimeter vertical without atmosphere corrections in ideal observation environments. And BeiDou significantly contributed to the reduction of scintillation effects, and Fugro is further improved the surface performance in challenging observation environments for border applications.